millions of cars quietly reach the end of their lives. Some are damaged beyond repair in accidents. Others simply grow old, inefficient, or too costly to maintain. Instead, it begins a second life inside one of the largest and most powerful recycling systems in the modern world. Today we're taking you inside a supergiant scrap car recycling plant, where old vehicles are dismantled, shredded, separated, and reborn as brand new steel that fuels America's industries. The history of car recycling in America goes back more than a century. In the early days of automobiles, scrap cars were often abandoned, stripped by hand, or left to rust in junkyards. Steel was cheap, environmental awareness was low, and recycling was driven mostly by necessity during wartime. During World War II, scrap metal became a strategic resource, and Americans were encouraged to turn in old cars to support the war effort. That moment marked a turning point. After the war, as car ownership exploded, so did the volume of vehicles reaching the end of their useful life. By the mid-20th century, specialized auto salvage yards and metal recyclers began transforming scrap cars into a reliable source of steel. Today, car recycling is not just an environmental choice, it's a cornerstone of America's industrial economy. In modern America, between 12 and 15 million vehicles are recycled every single year. That makes cars the most recycled consumer product in the country. On average, more than 85% of a vehicle's weight is recovered and reused. Steel, aluminum, copper, plastics, rubber, almost nothing goes to waste, and it all starts the moment a car enters a recycling facility. The process begins at auto salvage yards, where end-of-life vehicles arrive by tow truck from dealerships, insurance companies, auctions, and private owners. At first glance, these yards may look chaotic, but they operate with careful organization. Each vehicle is logged, identified, and prepared for depollution, one of the most critical steps in the entire process. Before a car can be crushed or shredded, every hazardous fluid must be removed. Workers drain fuel, engine oil, transmission fluid, brake fluid, coolant, and refrigerants. Batteries are removed, airbags are safely discharged, and electronic components are extracted. This step protects workers, equipment, and the environment, ensuring nothing dangerous enters the recycling stream. Once depollution is complete, valuable reusable parts are removed. Engines, transmissions, alternators, doors, wheels, and electronics are carefully dismantled and sold into the used parts market. This reuse phase alone keeps millions of affordable parts available for repairs, extending the life of other vehicles and reducing the need for new manufacturing. Only after reusable components are recovered does the remaining vehicle body move forward, now stripped down and ready for its transformation. The next stop is the crusher. In a matter of seconds, a full-size car is compressed into a dense steel cube. These crushed vehicles are stacked and transported to the heart of the recycling operation, the shredder plant. Here is where the scale becomes truly jaw-dropping. Industrial shredders stand several stories tall, powered by motors producing thousands of horsepower. When a car enters the shredder, massive rotating hammers tear it apart with explosive force. Steel, aluminum, glass, plastic, rubber, everything is shattered into thousands of fragments in just moments. What comes out of the shredder looks like chaos, but this is where advanced technology takes over. The mixed material flows onto conveyor belts and enters a sophisticated separation system. Powerful magnets instantly pull out ferrous metals, primarily steel, forming the backbone of recycled metal production. This steel stream alone accounts for millions of tons per year and is the primary reason scrap cars are so valuable to American steelmakers. Next comes non-ferrous separation. Eddy current systems use magnetic fields to eject aluminum and other non-magnetic metals from the stream. Optical sensors and air classifiers sort plastics, foams, and fibers. Copper wiring is recovered for reuse in electrical applications. Even rubber from tires finds new life in asphalt, playground surfaces, and industrial products. Step by step, what once was a single vehicle becomes dozens of reusable material streams. The recovered steel is then processed, cleaned, and compacted into massive bundles or shredded steel scrap. From here, it travels to steel mills across the country. In electric arc furnaces, recycled steel is melted at extreme temperatures and refined into new steel products. This recycled steel becomes the raw material for construction beams, rebar, appliances, tools, and even brand new cars. In fact, much of the steel used in modern American vehicles comes directly from old ones, completing a powerful circular loop. The environmental impact of this process is enormous. Recycling steel from scrap cars saves about 74% of the energy required to produce steel from iron ore. It reduces mining, lowers carbon emissions, and conserves natural resources. Every ton of recycled steel saves thousands of pounds of raw materials and significant amounts of water and energy. In a world facing growing environmental challenges, scrap car recycling is one of America's quiet sustainability success stories. Behind this massive operation are skilled workers and engineers who keep the system running smoothly. Operators monitor shredders and separation lines around the clock. Maintenance teams ensure machines capable of destroying cars every few seconds continue to function safely. Data systems track material recovery rates to maximize efficiency. What once was a scrapyard industry has evolved into a high-tech recycling powerhouse. Perhaps the most remarkable part of the scrap car recycling story is how invisible it is to everyday life. Drivers trade in old vehicles without thinking twice. New cars roll off assembly lines without revealing their recycled origins. Yet beneath the surface, a vast industrial network is constantly at work, turning yesterday's vehicles into tomorrow's infrastructure. A car that once carried a family across highways may now be part of a bridge, a skyscraper, or another vehicle entirely. Steel forged from scrap cars becomes the backbone of modern civilization, proving that even in an age of constant consumption, renewal is possible. If you enjoyed this inside look at one of America's most powerful recycling industries, make sure to like, subscribe, and turn on the notification bell. We'll continue exploring the massive processes that turn waste into resources and keep the modern world running. Thanks for watching, and as always, stay curious. Every modern battlefield depends on a machine that combines power, protection, and precision. The main battle tank, Designed to move over rough terrain, withstand enemy fire, and deliver devastating firepower, it is one of the most complex land vehicles ever created. But behind every tank rolling into action lies an extraordinary story, one of metallurgy, mechanics, and military-grade engineering. From hardened steel plates to multi-ton rotating turrets, each component must be crafted with extreme precision to survive the world's harshest conditions. In this documentary, we go inside a cutting-edge defense manufacturing facility to uncover how modern tanks are made. You'll witness how raw metal is forged into armor, how engines with over 1,500 horsepower are assembled, and how advanced electronics give these giants their strategic edge. This is not just about machines, it's about mastery. Let's explore how tanks are built, from armored plates to battlefield powerhouses. Every tank begins with its most critical feature, armor. Unlike ordinary steel, the plates used in tank construction are engineered to withstand high-velocity impacts, extreme temperatures, and explosive forces. The process starts with specialized armor-grade steel, known as rolled homogeneous armor. This high-strength alloy is made by melting iron ore with carbon and other elements like manganese, chromium, or nickel, depending on the required ballistic properties. The molten steel is poured into molds, then rolled into thick slabs under immense pressure to refine its grain structure and eliminate internal flaws. These slabs are then cut and shaped using plasma cutters and CNC machines to match the tank's unique dimensions. At this stage, the steel might undergo heat treatment, a series of controlled heating and cooling cycles, to enhance its hardness without compromising ductility. To increase strength without adding excessive weight, the armor is often assembled in layers, combining different materials such as ceramics, composite panels, or explosive reactive armor, ERA. These modular layers are precisely engineered to absorb, deflect, or disrupt incoming projectiles. Robotic welding arms are used to assemble the main hull. Precision is vital. The seams must be strong, but also smooth, to reduce weak points and maintain structural integrity. Once the structure is formed, the entire shell undergoes non-destructive testing. Ultrasonic and X-ray inspections reveal internal defects. Impact testing ensures resistance to simulated battlefield conditions. Only after passing all tests does the armored hull proceed to the next phase, becoming the mobile foundation of a fully operational battle tank. With the armored shell completed, attention turns to the foundation that gives the tank its mobility and power: the hull and powertrain. The hull is the lower portion of the tank, housing the driver's compartment, fuel tanks, transmission, suspension system, and the engine bay. Engineers begin by fitting internal structural supports into the armored shell. These supports add rigidity and create defined zones for each system. Next comes the installation of the powertrain, a powerhouse capable of moving a 60-plus ton vehicle across mud, sand, or rubble. Most modern battle tanks, such as the M1 Abrams, use either a 1,500 horsepower gas turbine engine or a turbocharged diesel engine. These engines are pre-assembled in a clean room, then carefully lowered into the hull using an overhead crane. Connected to the engine is a heavy-duty automatic transmission designed to handle massive torque while offering multiple gear ratios for both combat and cruising. This transmission is coupled to a drive shaft system that channels power to the drive sprockets located at the rear of the tank. Suspension is another critical system. Tanks use torsion bar suspension or hydropneumatic systems to absorb shocks from uneven terrain. Each road wheel is attached to a torsion bar, which flexes under load, providing a smoother ride for both the crew and the sensitive electronics inside. The wheels are then connected to the track system, made from interlocking metal segments with rubber pads. Tracks are assembled on-site, then stretched around the drive sprockets and road wheels. The result? A continuous loop that distributes the tank's weight evenly, allowing it to traverse almost any surface. Once assembled, all mechanical systems undergo extensive bench testing. The engine is started, transmission cycled, and tracks rotated at various speeds. Engineers monitor oil pressure, temperature, and vibrations to detect any early faults. Only when the tank's mobility systems pass every test does it advance to its next evolution, receiving the firepower that defines its battlefield presence. If the hull is the backbone of a tank, the turret is its muscle, housing the firepower, optics, and targeting systems that define the tank's combat capabilities. Construction of the turret begins with a circular armored shell, fabricated from high-strength steel and composite armor. Just like the hull, its walls are designed to deflect or absorb the kinetic energy of incoming rounds. Advanced tanks may also include explosive reactive armor, ERA, panels, which detonate outward to neutralize incoming projectiles. The heart of the turret is the main gun, usually a smoothbore cannon ranging from 120mm to 125mm in diameter. Made from high-grade steel, the barrel undergoes precision forging and rifling if required, followed by stress relief heat treatments to ensure durability and accuracy under extreme pressure. The cannon is mounted on a gun cradle, which connects to the elevation and recoil systems. These allow the barrel to move vertically and absorb shock during firing. Below the cradle is the autoloader system, used in many modern tanks to automatically chamber shells from a rotating magazine, increasing rate of fire and reducing crew size. Surrounding the gun is an array of advanced optics and targeting systems. These include thermal imaging cameras for night and low visibility conditions, laser rangefinders to calculate target distance with extreme precision, ballistic computers that account for wind, movement, and angle of fire. These components are wired into the tank's fire control system, FCS, which calculates the optimal firing solution in milliseconds. Many modern turrets are also equipped with stabilizers, allowing accurate fire while the tank is on the move. The turret is mounted onto the hull via a turret ring, a reinforced bearing system that allows full 360-degree rotation. Heavy-duty motors power this rotation, controlled from within the crew compartment. Once all internal components are fitted, the turret is hoisted by crane and carefully aligned with the hull. Final calibrations ensure that electronics, hydraulics, and mechanical linkages are perfectly synchronized. With the turret in place, the tank is now a fully armed combat machine, ready for battlefield testing, but not yet complete. Next comes the nerve center, electronics and control systems. While steel and firepower give a tank its strength, it's the electronics and control systems that give it intelligence and precision. Inside the armored shell, a network of advanced electronic modules manages everything from targeting to navigation. At the heart of this system is the fire control computer, a ruggedized processor that takes real-time input from sensors, rangefinders, gyroscopes, and environmental data to calculate the perfect firing solution in fractions of a second. The gunners and commanders' stations feature multifunction displays, joystick controls, and high-resolution targeting optics. These are linked to thermal and infrared cameras, allowing the crew to detect threats in complete darkness through smoke or in adverse weather. Navigation is handled by an integrated inertial navigation system, INS, combined with GPS, giving the crew precise awareness of location and terrain. This is essential for coordinating with allied units and avoiding known threats in the battlefield. Communication systems are also critical. Each tank is equipped with secure digital radios, allowing encrypted voice and data exchange with other vehicles and command posts. Some platforms even support network-centric warfare, linking into larger battlefield networks for real-time intelligence sharing. To manage all these systems, the tank features a central power distribution and control module, ensuring that electrical loads are balanced and protected. Backup batteries and redundant wiring prevent system failure during combat. Modern tanks may also integrate active protection systems, APS, using radar, cameras, and microprocessors to detect and neutralize incoming projectiles before impact. Once installed, all electronics undergo diagnostic tests to ensure accuracy, synchronization, and combat readiness. With electronics in place, the tank is nearly complete. What follows is a crucial test of everything working together. Real-world trial runs. Before a tank can be deployed, it must prove itself through rigorous testing, both in the lab and in the field. The completed vehicle is first subjected to static inspections. Technicians check wiring integrity, fluid levels, weapon alignment, and system calibration. The turret is rotated, the gun elevated, and all hatches operated to ensure mechanical soundness. Next, the tank is moved to a test track, a simulated battlefield environment with mud, water obstacles, steep inclines, and rocky terrain. Here, the engine is pushed to full power, the suspension is stressed, and the tracks are tested under real-world loads. Every vibration, temperature change, and fluid pressure is recorded. The tank then undergoes live fire testing. Operators fire the main cannon at various targets, measuring recoil behavior, targeting accuracy, and reload cycle times. Onboard sensors capture data while technicians observe remotely. Only tanks that pass all mobility, firepower, and electronics tests proceed to the final stage. Once verified, the tank enters final assembly. Crews install exterior components such as camouflage panels, radio antennas, smoke grenade launchers, and field tools. The exterior is painted using infrared deflecting coatings, reducing visibility to thermal imaging. Interior systems like fire suppression, storage compartments, and crew comfort features are finalized. Each tank is then assigned a serial number, recorded in a database for maintenance tracking. Finally, the completed tank is loaded onto specialized transport vehicles or rail platforms and shipped to its designated military unit. What began as raw steel and scrap has now become a fully operational battle tank, a fusion of engineering, firepower, and innovation, ready to defend and dominate in the world's most demanding conditions. Enjoyed this deep dive into how battle tanks are made? There's more where that came from. On this channel, we uncover the hidden engineering behind the world's most powerful machines, from factory floors to front lines, from molten metal to military-grade precision. If you are passionate about how things work, how raw materials become advanced technology, and how innovation shapes modern warfare, hit that subscribe button now and tap the bell so you never miss our next documentary. Your support helps us keep creating high-quality, ad-friendly videos for curious minds like yours. Let's keep exploring the machinery that moves the world.